Hello everyone. Thank you for joining DataCon LA 2022. Welcome to AI/ML Data Science Track. My name is Veeti, your host, and our co-hosts today are Sadna and Nikhil. Please silence your phone during the session and don't hesitate to raise your hand if you have any questions. This session is currently streaming via Zoom and will be recorded. It will be available online in few weeks. Today we have our guest, John Thorpe, and he will be talking about the BreezeML approach to affordable ML. Now, without further ado, I'll hand over to the speaker. Thank you for being here.
Thank you. Okay, hi everyone. So my name is John Thorpe, and I'm the head of product at BreezeML, a startup that is attempting to make AI affordable and managing infrastructure easy. Thank you all for coming to my talk. And today we're going to talk about using the cloud to make AI affordable, low, and easy to deploy. So just a quick introduction of our founding team. We are founded by a group of researchers from both UCLA and Princeton. And Harry and Ravi are both professors who have made many recognized contributions to the field of computer science. Pungjan is a student who is currently doing his thesis on machine learning systems, but has had plenty of industry experience in machine learning and cloud, as well as machine learning optimization. And I recently graduated from UCLA and built my thesis specifically on utilizing the cloud to enable affordable training of large machine learning models. So our team has many years of research experience in machine learning systems, and we've worked across a wide range of different domains, from vision models to language models to even newer models like graph neural networks. And we've been mainly focused on the optimization of performance in distributed settings. So our talk today talks about utilizing machine learning for businesses and bringing down those costs. And this is specifically important because more and more companies these days are trying to find ways to incorporate machine learning into their business workflows to automate different processes. And they are finding new and innovative ways to do this in everything from logistics to healthcare to banking. And for many small and medium-sized companies, in order to do this, they have to largely rely on the cloud, as spinning up in-house infrastructure is very expensive and difficult to scale as the business scales. So for many of these businesses, what they want to focus on is developing models and integrating those models into their business workflows, not specifically focus on managing the infrastructure and the distributed training that is needed to develop those models. And this is, for a lot of different companies these days, AI costs are rising, and if not already very high. So many companies can have spending in the millions of dollars per year on the cloud, specifically for machine learning infrastructure. And this is especially true of companies who are very focused on providing AI as a service, such as self-driving companies. And for a lot of smaller companies, the expenses associated with starting AI initiatives can be a real setback in terms of exploring these different initiatives. And this is all made worse by the fact that with modern models, the requirements to train them or run inference is getting even worse. So if we look at something like GPT-2 to GPT-3, the shift resulted in significantly higher accuracy and better performance of the model, but also significantly higher costs. So it went from tens of thousands of dollars to over $10 million to train. which is very out of reach for many small to medium-sized businesses that may want to experiment with these types of models. So just to give a quick visualization of this trend in action, we can see on the left the size of models increasing over time exponentially. And this is measured in the billions of parameters. So as you can see, GPT-3 recently is still a very massive model with hundreds of billions of parameters. And as mentioned, took many millions of dollars to train. But even so, Google has released models that are even larger, hitting trillions of parameters. And so the number of parameters is generally proportional to the amount of resources or the compute time needed to train these models. And it should be noted that even for more regular sized models that can fit into a single GPU, the sizes of their data sets are also increasing. So,
the slides are not being shared.
I see. You can change the share screen, right? Thank you.
Just minimize this.
Yeah. So so basically even data sets are growing rapidly, which increases the amount of time needed to train. And on the right, we can see what happens when you have these growing data sets and model sizes, which is that the infrastructure to support them inherently has to become very complex and distributed and requires a lot of money to support the inference and training. So in addition, at scales like this, managing infrastructure and communication can become very difficult, requiring things, for example, applications need to be written in a way where they consider the distributed architecture of training. For example, pipeline parallelism, where we take a particular model and we split it up among a bunch of different workers, or model parallelism, where we split the operators of a model to allow models to expand beyond the memory of a single GPU. And in addition, there's the data parallelism, which is the most common way of using parallelism, in which case the model is replicated among a series of parallel workers to allow throughput to increase or allow the batch size to increase. And the point in all this is basically to say that these are very complicated things for developers and data scientists to have to take into account when all they're trying to focus on is the quality of the model and making sure they get the most out of their data. So our goal is to help address some of these issues by bringing down the financial barrier for AI by reducing the costs of ML workloads and doing so while preserving existing programming interfaces and compatibility with existing tools to preserve existing pipelines. And that would allow data scientists to focus on reducing the costs of their ML workloads without having to focus on without having to put in excessive effort to take advantage of these savings. And also to manage resources carefully to make sure that for jobs that have specific requirements like SLA guarantees or accuracy targets, that we can still meet all of these targets effectively. So how do we go about achieving this? And this is where some of our years of researching and playing around with these different models and cloud computing comes into play. So some things we've noticed over the years is, for example, GPUs can have very different characteristics depending on the model. For example, if you take a modern, very performant V100 GPU, it can get very high throughput on transformer-based models. But when you normalize it by cost, the cost normalized throughput could actually be lower than other older GPUs with lower performance, which can change considerations if you're more of a cost conscious, if you're more cost conscious about your workloads. In addition, we have also experimented with incorporating serverless into different ML pipelines. And specifically today, we're going to talk about how BreezeML uses spot instances to reduce the cost of training. So for those of you who don't know, I'll just do a brief recap of what are spot instances. So spot instances are servers usually available on almost all public clouds, and that can be you can get at up to a 90% discount because they are utilizing idle capacity in the data center, and they still have equal performance to their fully priced counterparts. However, they can be taken away at any time. So preemptions can be preempted by the cloud provider at any time, dependent upon capacity constraints, or if a price has been specified by the user. And this happens much more frequently than in typical cases where for things like hardware failures, which constrains how they can be used, at least easily, to more stateless jobs that can be quickly stopped and restarted. So there is a very simple way that's been developed to handle these kinds of failures, which is checkpointing. And just to quickly recap, is basically when during training, we train to some particular point, let's say step I, and then we checkpoint that model to some storage. And then upon continuing training, if we have a failure, we can bring up a new worker and load the model at that checkpointed step, and then continue training from there. And so this has been used a lot, but we have done some experiments and found that when running larger models, there can be cases where spot instance preemptions start happening very frequently, especially when demand for nodes starts to rise at particular times throughout the day, for example. And this can lead to a lot of turnover in the number of instances that you have in a training cluster. And so here we can see over the course of a several-hour run, training GPT-2 with 64 spot instances. The blue is the time where training progressed and we were able to save a checkpoint. Orange is where the cluster progressed, but maybe we weren't able to save a checkpoint. And red is the cluster is having to restart and reconfigure, which means it has to rendezvous and find whichever nodes still remain in the cluster. And all of these things end up taking time. And so that's why with something like this, we found that checkpointing can actually lead to a lot of wasted time for a training cluster. So we're developing our product, which is an ML platform as a service that exists across many different levels of the stack. So one of the main things we provide is our plugins for many different popular frameworks, which also interact with our resource manager at the lower levels of the stack, which include a scheduler and a runtime, which are designed to make decisions about how to provision resources effectively depending on the job. So it is designed to understand the constraints of a user's job and intelligently provision resources to match those needs. I'm going to start out first by talking about the plugins and how they allow us to achieve resilience and elasticity when training on transient nodes. So the question is, if checkpointing can't always work, how can we provide faster recovery and maintain accuracy of the model? So one way to do this is to introduce redundancy into the pipeline. So this is, for example, let's say if we're training a model in a pipeline parallel configuration, like I mentioned earlier, we could slightly over provision the number of instances so that we have redundancy. And this way, when we encounter some failure, it is much faster to simply reroute the pipeline and continue training. However, this obviously can incur a fair amount of overhead because producing fully duplicate pipelines, training pipelines, wastes a lot of resources. And so there's a question of how we can do this more intelligently so that we can maintain robustness while minimizing these excess overheads. So one thing we can do is we can co-locate the different stages of a pipeline together so that we can utilize data locality and avoid network transfers when two stages need to communicate. And this also helps because now, in the case of a failure, so instead of having to go to a separate instance entirely, we can simply reroute within the existing pipeline and continue training from there. So even with this though, it is important to note that with co-location, we may still add overhead from trying to synchronize the different components and therefore add training overhead to the training. And so this is where we can take a closer look at things like pipeline parallel models and how they work to understand exactly how we can improve this. So for example, when we run large models like this in a pipeline parallel configuration, we divide a mini batch into a set of micro batches. And each of these micro batches has to be passed down the pipeline to the different nodes consecutively. And as there's communication between the nodes, this also results in stalls. So as you can see here, there's this bubble in the middle of the pipeline. And it should be noted that this is an example of a fairly naive pipeline schedule, simply to demonstrate the idea of a bubble in a pipeline. But in more recent, more sophisticated pipeline schedules, the bubble is minimized, but it still exists. So this is something more like what a realistic pipeline schedule would look like with idle periods interspersed throughout the training. And so this is sort of an inherent part of training that there's not really a lot you can do to get rid of these idle periods. And so we asked if there's a way that you can use these idle periods to introduce your redundancies without having to add that overhead that we added earlier. So for example, we can synchronize with other nodes or pre-compute values so that when we do encounter a failure, we now have the quick fallback that we can fall back onto without having to incur extra time to perform that redundancy. So this is an idea of how BreezeML is using stalls and inherent communication blockages and pipelines to increase resilience while training on elastic nodes. And it should be noted that I used pipeline parallelism here as a very specific instance of this, but that the insights and the key techniques do apply for more general parallelization techniques. So as mentioned, there's multiple levels in the stack to our product. So this was our plugins, which work at the framework level to assist with elastic training. But we do also provide our resource manager, which operates more at the infrastructure level. So our Breeze resource manager is a component that continuously monitors the nodes to make sure that we are maintaining the amount of nodes specified by a user. So for example, if they've specified some constraints about either cost or performance, then this will make sure we are intelligently selecting a mix of both spot and on-demand so that we can meet these requirements even while nodes are coming and going from the cluster. And so putting all this together, we measured the effectiveness of BreezeML over a wide range of popular models. And Specifically in this diagram, you can see the red line, which is an on-demand baseline, and the blue bars, which basically represent how BreezeML compares to these normalized to the baseline. And specifically here, we are measuring the performance per dollar. So basically what we wanted to understand was per dollar that you spend on computation, how much value were we able to provide in comparison to the baseline. And so this also leads into another problem, which is managing the highly diverse software and hardware stack that is common among ML pipelines. So specifically, we have a lot of heterogeneous platforms, and these have to interact with many different types of hardware resources. And across the clouds, there are many different types of pricing models. And as we move forward, this trend is likely to increase at both the bottom and the top levels of the stack. So as you can see, we have CPUs and GPUs, but then each company is also starting to develop their own custom chips. So we have Google's TPUs, AWS has Inferentia and Trainium. There's even Habana Labs Gaudi chips. So the hardware space is becoming increasingly heterogeneous and fragmented. And then there's on-premise clouds combined with the many public cloud providers, which more companies are running hybrid cloud deployments. And then the different frameworks as mentioned, as well as ML ops tools for managing training and inference. And so modern ML pipelines and data analytics pipelines can span many different aspects of this heterogeneous stack. And in addition, they can have different requirements, such as different hardware requirements, security requirements, or different constraints in terms of performance and cost. And so to handle these, BreezeML is building a platform to allow users to define complex jobs with minimal effort. So basically, they can provide a piece of code which describes each of the jobs in a pipeline with annotations that specify specific requirements, such as the type of hardware that needs to be used, security constraints, and cost and performance. And we can compile these into a data flow graph, which can then be partitioned and placed among different clouds or different resource backends, depending on which one would provide the most optimal cost or meet the user's constraints most optimally. And so initially, for an initial allocation, we can use something like historical data about previous similar jobs and how they've performed under different circumstances. But we also have a job monitor, which continuously analyzes the jobs and collects job metrics to make sure that we are meeting the performance requirements, and can then repartition and reallocate tasks if needed. So to use BreezeML, we provide two different ways. There's the Windmill machine learning platform, which is a fully managed platform for data scientists that don't want to manage infrastructure. And then there's also Lattice, which is the Kubernetes-based framework, which has our plugins, our Kubernetes operators, and our integrations into things like Kubeflow. And we have a few different pricing models depending on the customer. But in conclusion, we are utilizing cheaper resources on the cloud more accessible and reducing developers' needs to understand the underlying infrastructure that runs their ML workloads, and allowing developers to make full use of the heterogeneous tech stack. Thank you.